In the previous lecture and in your discovery, we are finding the approximate values of trig functions by plotting them on a grid system and then approximating. So if I was to look at this grid system, I can tell that, remember, those are tenths. This is 1 comma 0. That is an exact value. And we related the cosine with the x-coordinate and the sine with the y-coordinate. So what's happening here is you were to draw, let's suppose, a 45-degree angle. And you were finding the x and y coordinate, and you approximated it with about 0.71. And again, that is a 45-degree angle. Well, because that's approximate and we want exact values, that's why this is called the exact values, we're going to go back and use this idea of SOHCAHTOA on a triangle that I'm going to draw over here. It's called an isosceles triangle. And an isosceles triangle, that's a C in there, isosceles triangle has two sides of the same length, and we're going to call this an isosceles right triangle because those are the types of triangles we've been dealing with. So I'm going to draw a triangle in which the two sides are equal length. Using Pythagorean, I know 1 squared plus 1 squared equals c, the hypotenuse squared. So c is equal to 2, c squared is equal to 2, or c is equal to the square root of 2. These are 45 degrees because from our first discoveries, we found Pythagorean. We also found that all the angles of a triangle add to 180. So if this one's 90 in this bracket, this little square here, the other two must be 45 because they open to legs of the same length. So we call this a 45, 45, 90 triangle. So if I was now to find the sine of 45 using this idea of SOHCAHTOA, 45, the side opposite, is 1. The hypotenuse is the square root of 2. And if I was to use my calculator on that, which I'll call up here, and plug in 1 over the square root of 2, we'll see if it isn't approximately that idea of 0.71. So I'm taking 1 divided by the square root of 2. And I get that value. Notice I had to round it here, but these tenths are pretty darn close to what the calculator said. I could have also tried my calculator, but you're going to have to do these without a calculator. And notice I get the same value. So to find the exact values, we're going to have to use these triangles instead of just estimating off my unit circle. However, it looks like I can find the exact values at these 4 locations. So I'm going to go ahead and label those. This looks like 0, 1. This is -1, 0. And this is 0, -1. So it looks like those 4 coordinates are exact and the rest of them are approximate. I can do the same thing with a 30, 60, 90 triangle, but I first of all have to come up with that triangle and some side measurements. So this is going to come from an equilateral triangle. So I'm going to draw an equilateral triangle. That just means all 3 sides are the same length. And if all 3 sides are the same length, that just means all angles are the same measure. They're all 60. Well, notice I need a 30, 60, which I have, and a 90. So if I bisect this angle, half of 60 is 30, and here's my 90. So there's my 30, 60, 90 triangle. So because I cut a side in half, we could use any measurement we want, but an easy number that would be to cut in half for me might be 2. So I'm going to call this side 2. Well, half of that would be the base here, which would 1 because I split that angle, and then I again would use Pythagorean. So that's why it was so important at the beginning that we got Pythagorean theorem figured out. And it says if I wanted the 2 legs, the missing leg is equal to the hypotenuse squared. If I move the 1 over, I get b squared equals 4 minus 1, which is 3. So b is the square root of 3. So now I have this 30, 60, 90 triangle in blue and green. So again, if I took and measured a 30-degree angle in green in my circle up here, and I used my protractor, and I measured where it would be, this is a 30-degree triangle. And if I go ahead and measure, I see that this is about 0.86 and that's x, and this distance here is 0.5. Let's see if that's the same thing. So if I go and I find the sine, and we're dealing with a 30-degree angle, I can see from my triangle in my circle, it should be about a half. Well, let's see if that's true on my triangle that's outside my circle, that's no longer in a unit circle. So if I go to 30 degrees and I do my SOHCAHTOA, I'm using sine. Side opposite is 1, and the hypotenuse is 2. So it looks like that matches half, 0.5. What if I did the cosine of 30 degrees? The cosine of 30 is a side adjacent, which is the square root of 3 over 2. And if this is going to work, we need that to be about 0.86. So let's go ahead and call it the calculator. And again, I'm doing the square root of 3, and I'm dividing it by 2. And I get this 0.8667, and that's very close to my approximate on my unit circle, and it's exactly the square root of 3 over 2. So that's why we call these exact values versus the approximate on my circle. Let's check it another way. If I type the cosine of 30 degrees in my calculator, notice I get the same value. So we can find it on our circle, we can find it on a triangle, and we can find it in our calculator. Let's check the sine of 30. And once again, notice that was 0.5. I was exact on my circle. If I had drawn my angle exactly, it would have had 5 units up. Okay, so that is the difference between approximate and exact values.